Hello, everyone. So today we're going to continue our conversation about phase diagrams by looking a little bit more closely at the liquid phase and what sort of interactions may happen at the liquid-liquid level. So not too surprisingly, a good place to start is looking at the thermodynamics of mixture. And for that, we can go back to our good old friend, the regular mixture. So again, in an ideal regular mixture, what we end up finding is that with no preference of IMFs in between A and B, as long as they mix similarly, what we find is that there is always going to be the most preferable mixture is always going to be the 50-50 mixture. Because again, in this case, since A has no better IMFs with B than with itself, it's going to tend to follow entropy, which gives us the mixture with the most possibilities. Again, an even mixture when you never know who you're going to be next to. So again, for any ideal solution, they're always going to be miscible, and the most favorable state is always going to be the perfect 50-50 mixture. However, things get a little bit messy once you get to a real solution, because at this point, there's going to be a certain preference of IMFs of one species with another. And we're only going to find miscibility if there's only one free energy minima present, just like for the ideal case. Because what's going to end up happening is that, again, for a regular system, we can observe that as the two systems have essentially weaker and weaker IMFs, more or less as A tends to prefer itself more over interacting with B, what we're going to find is an increase in the interaction energy given by psi. So in this case, as our interaction energy starts increasing, what we're essentially doing is adding a repulsive term over this even mixture, because more or less they don't want to be hanging out with each other. They'd much rather hang out with themselves. And that's really where this energetic penalty comes from. And it gets more and more significant the more dissimilar their IMFs become, until you reach essentially kind of this critical point around a psi of 2, at which point we kind of lose our minima. We have kind of this flat interaction, so it's equally favorable to have a mixture anywhere from about 0.4 to 0.6. Unfortunately, once your psi gets greater than 2, what we find is there's now an energetic penalty for a perfect mixture, simply because it's too much to ask A to hang out with that many molecules of B. And what we end up finding is above this point, we find 2 minima a little bit further out. And one way of looking at this is what we have is 2 contaminated phases appear, where I've got one phase that's rich in A, but poor in B, and a second phase that's rich in B and poor in A. So again, one classic example of this is the good old example of oil and water. Oil being very hydrophobic and water being the very definition of hydrophilic, don't like to hang out with each other. But if you mix oil and water, you'll always find there's going to be a little bit of oil in the water and a little bit of water in the oil, because there's just no beating entropy. Entropy will always dictate some extent of mixing of liquid phases. We can actually see this by looking at a liquid-liquid phase diagram, because what we're going to observe is very similar behavior to this, where there's going to be at some high temperature, all phases tend to essentially look alike. So essentially, just like we saw with gases, at high speed, everybody's the same. And we're going to similarly find that everybody's miscible if you get to high enough temps. However, below a point at which is called the upper critical point, we're going to find our phases separate out. At this point, what we'll end up finding is, say in this example of nitrobenzene, in hexane, what we find is below this upper critical point, it's going to split into a nitrobenzene rich phase and a nitrobenzene poor phase. And the question here is how can you figure out if I have a given composition uh, of my starting mixture and I say cool it down to a point at which it separates, how much is going to be in the nitrobenzene poor versus the nitrobenzene rich phase? And for that, it turns out we have a good old friend, and that's going to be the lever rule. Because again, all the lever rule cares about is that I have some sort of unstable mixture that splits into two phases, at which point all you need to know is how far you are away from those equilibriums. The ratio of the distance will give you the ratio of the moles in each of the newly generated phases. And so what's very important to realize is that when I say take this mixture of nitrobenzene and hexanes, I don't generate a nitrobenzene phase and a hexane phase. I generate a nitrobenzene rich phase and a hexane rich phase. These are still mixtures. They're just mixtures with two different components. And so when you see a diagram like this, we're looking at a phase separation. But here's going to be the real trick. How can I predict when these phase separations occur? Well, let's go ahead and revisit our regular solution. So again, for a regular solution, we can predict the free energy of mixing using our expression in terms of the mole fraction of each of the components and the strength of the intermolecular forces between the species. Now, one of the important things to remember is that, again, we're going to see a phase separation if I have more than one minimum value. So how am I going to predict when a minima will occur? Well, we have our good old calculus phrase. A minima is going to occur when the first derivative can be set equal to 0. And since we're looking at when a minima occurs with respect to composition, we're going to take the first derivative with respect to the composition of A here. Now, you may notice that this guy's going to get a little bit messy because this term out front is a constant and we can pull it out. We have a dependence on A here, 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 and here, which isn't going to be made any easier because we're going to have to substitute in a 1 minus the mole fraction of A for each of these XB terms. So it turns out that this isn't too bad, but it's going to involve a lot of product rules. So either you can have a lot of fun doing that, or I can just provide you the pre-solved equation, which is more or less going to give us a natural log of the ratio of the mole fraction of A to the mole fraction of B is going to be equal to a strength of the intermolecular forces times essentially 1 minus the composition of the species. So now all we have to do is try and solve for the mole fraction. However, we do run into a slight problem. As it turns out, there's no analytical solution for the mole fraction in this case. So we have to essentially use a older, kind of a little bit more fun trick, which is a graphical solution. So what I can do is I can plot two lines. One is going to be a natural log expression, and one is going to be a straight line based on the mole fraction of A. And when we do this, we're going to generate a series of lines. So it's worth noting the natural log expression is always going to generate the same curve because it has no dependence on the strength of the intermolecular forces. However, these straight lines will actually have a dependence. And so we can imagine drawing several lines with different strengths of the intermolecular forces. Again, one denoting the two species don't mind each other that much. 4 indicates a rather significant dislike for each other. In other words, A would much rather hang out with A than have anything to do with B, because in this case, it turns out A is a snob. So when we do this, we can end up finding that it turns out there's actually no solutions for a psi value of 0, which again makes sense because it's only going to cross through this 0.5 point, which in our case would indeed be a minima. But for our intensive purposes of looking for minima, this is going to be our maxima. So we're going to ignore any trivial solutions of 0.5. We also don't have any solutions for 1. And 2, we run into this unique places where actually the lines, our straight line is the tangent of our curve and not actually a solution. But that means that for any value of psi greater than 2, we start generating intersections. And we'll always generate essentially 2 intersections, as we'll generate 2 new, more stable minima. And so what we can do is then by plotting these minima, this is going to give us essentially at which point I will now generate the stable mixture. And so what we're going to tend to do is form 2 mixtures of the given compositions. So for example, if I have a psi of 3, I expect to form one mixture with a mole fraction of A of about 0.9 and one with a mole fraction of about 0.1. And again, it is worth noting this assumes a regular mixture, so even mixing, which may not always be quite the case. So in practice, if we go back to our nitrobenzene phase, what we end up finding is something interesting, which is that our compositions change with temperature. And by the very nature of this, what it tells me is that the nature of the intermolecular forces also end up changing with temperature. And again, this should make a certain amount of sense because as I increase the temperature, I'm giving the system less and less time to see each other, which if I'm trying to mix something is actually quite good because everything looks similar at high temps. And as I go to lower temps, they have more of a chance to see each other's intermolecular forces, which for most mixtures tends to mean that I'm going to have a much larger value for psi at lower temps and thus a greater separation. And the identities of my 2 stable phase mixtures are going to be very different. And again, it's worth noting that this case of forming a upper critical temp is going to be fairly common and most common where we have significantly different IMFs. So again, things like a polar system like nitrobenzene, well, it has a little bit of a nonpolar edge, which lets it be mildly miscible in hexane. It still is too polar to be readily miscible. And again, old friends like oil and water. Down to some systems that are pseudo-stable, such as fatty acids in water, which again have some polarity, but still a fairly large nonpolar chain. However, one of the things that's worth noting is if this system were to be truly regular, we'd expect to see a symmetric shape to the curve. However, it's worth noting that many systems do show this degree of asymmetry, which is often exhibited in a system where we have uneven mixing, thus a little bit more unpredictable entropy of excess, thus a slightly skewed form. However, one of the things that's worth noting is that while it's fairly easy to think of cases where we have significantly different IMFs, which will cause a phase separation, sometimes we run into more interesting cases, which are only able to mix under low temps. So you may have something like triethylamine and water. So you have triethylamine, fairly nonpolar, water, the definition of polar. But under very low temps, as they cool down, you can actually form a hydrogen bond in between the amine and water, and so they will actually form a mixture. However, as you heat the system up, now I'm not giving enough time for the water to find that good hydrogen bond, and it would much rather be lazy and go hydrogen bond with itself and separate out. And that's actually indeed what we see, is that some of these complexes form what's called a lower critical temperature. So they're able to often form good bonds at low temperatures. And then when heated, essentially they're much more likely to go for the easy option because they have enough energy to do so and will separate out into two phases. In this case, triethylamine will tend to form with itself, and water will also tend to form with itself, generating two phases. And you can again predict the ratio based on the lever rule. However, you can also imagine some cases where things get a little bit more entertaining, such as nicotine. So it turns out that when you mix nicotine with water, something interesting happens because nicotine has several nitrogens, which means it's able to form hydrogen bonds with water under low temps, specifically or below about 61 degrees. Uh, Nicotine is pretty much fully miscible with water, which is wonderful if you're trying to, say, make a vaping apparatus. However, something interesting ends up happening is you say heat the system up a bit. Most significantly, what ends up happening is that now the fact that nicotine is mostly nonpolar kicks in, and nicotine and water will separate out into two different phases. And this will essentially dominate over most of the range. However, as long as you keep the system under enough pressure to prevent volatility, then something actually very interesting ends up happening. If you heat it up high enough, well, now they're moving so fast they can barely tell who's who anymore. And so again, they're miscible. So it's entirely possible to have some species like nicotine and water, which are going to be miscible under low temps and high temps, but in between, they're going to essentially break apart due to their dissimilar intermolecular forces. And you can imagine that many systems like this might be of great interest to industry because in some cases, they may want them to be able to be mixed together to be packaged. However, if you're trying to volatilize nicotine, you'd probably want to go ahead and separate it out into its own liquid phase, which you can indeed do based on this phase diagram. However, one of the things that we're ignoring here is the fact that both water and nicotine are also fairly volatile. So if I've got two liquids that are slightly dissimilar but volatile, we're going to see many of these behaviors we've been describing come together. So under, say, a lower temp regime, these systems just might not like each other. So if I have a mixture of, say, A and B under this low temperature regime, it's going to separate out into a B-rich component and an A-rich component. And this is going to happen until I say heat it up enough that now they're essentially warm enough. I got a good mixture. Who doesn't love this in cooking? It's how you essentially get things, get all your flavors to go into maybe solvents they don't like, whether it's a polar fragrance moving into oil or a non-polar fragrance moving into water. Heat will cure all. However, one of the things you have to watch out for is if you heat it up too much. Because if you heat it up too much, then we have to worry about our good old friend, volatility. And at this point, what we end up finding is the system will essentially separate out. And so if I take this system of A1, where now it's a perfectly miscible system, I'm going to boil it, collect the vapor, condense it back down into a liquid, keep on cooling it back to the same temperature I started with, and I'm going to generate two different phases of the liquid. One is going to be a liquid slightly richer in B than I started with, and one is going to be a component of liquid that's much richer. And you can also imagine this as another potential trick of how you might be able to move past an azeotrope by essentially, instead of trying to boil it out, try and use liquid-liquid separation instead. So if you have an azeotrope in the wrong place, look at maybe combining it with a different liquid so you can separate it past. So essentially, if heat doesn't work, maybe cool will. However, we also have to acknowledge what might happen if I've got two very volatile liquids. So what may end up happening if my liquids are too volatile, well, then this boiling point's gonna come down. And especially if they're very dissimilar, well, you can also imagine that liquid separation moves up to the point where we never actually form a liquid-liquid mixture. So I may have, say, a mixture of A and B that at low temps separates into two liquids, one B rich, one A rich. And then if I keep heating it up past a certain temperature, in this case about 320, well, here's the interesting point. If I'm below 3 or above 320, I'm no longer going to separate out into two liquids. I'm going to separate out into a liquid that's rich in B and a gas that's richer in A. Because what I've done is now I have to worry about boiling instead of just simply separating. And this is actually a fairly common occurrence, where instead of just making two different liquids or making a vapor in a liquid, I may end up walking past the point where either could end up happening, where either the liquids separate or I just straight boil it. And this all kind of revolves around a very important point with these types of mixtures called a eutectic point. So for example, this is called a binary eutectic mixture, where at this single point, I'm essentially slightly generating a little vapor, but not much, and the vapor has essentially the same composition as where I started. But if it also generates two different liquids, one's going to be rich in B, one's going to be rich in A. You can also imagine finding the eutectic point by, say, taking a liquid or taking a gas, condensing it down, and finding you generate two different liquids directly. And this is going to be also a very important point to examine, as this is also the lowest point the vapor can possibly go. And so you can imagine examining this by slowly increasing the composition of B in solution until it turns out that the boiling point can't go any further. So again, these eutectic type mixtures can be very important in many practical aspects. And in fact, we're going to examine the solid liquid case of it later in lab. But for now, we'll go ahead and next time talk about this, apply these same concepts to solids and liquids instead of just liquids and gases. Till then, take care.